you actually be dishonest. But that being said, welcome to the second day, also our second day of the hackathon. Today, we brought to you two very special people, two very special speakers. We are going to talk our jury, which are Madame Aicha and Monsieur Soufiane. They will give you their talk, and I understand it to be something that it's very interesting for you, but yeah, since we are gentlemen and we agree that we should be shoulders, we're going to start with Madame Aicha. So before we start with her, I would just like to mention that she is a third-year PhD student at the Göttingen
University, and also
as well,
DLR.
As well as a part of the group of the, you told me name, what was it?
Smart Mobility?
Yeah, Smart Mobility Group. They call it chair, by the way, which is a weird way to call things, but yeah. So, Madam Aicha, تفضلي مشكورة. Thank you.
Hi everyone. As it was announced, my name is Aicha. I'm now currently living in Germany, and today I will be talking about smart mobility, and specifically I will be discussing just one topic in smart mobility, which is the identification of transport means. And now I will just begin with like a short introduction of our group in DLR and what we're working on in general. So normally we know that mobility is a right, and everyone should be equally have the same accessibility for mobility, and it should have the right to go freely from wherever he wants and at whatever time he wants. And for the mobility to be smart, it needs to follow this like 4 certain rules. First, it should be accessible. So we should have transport means that they are accessible for everyone, not just like, we should not neglect the other people, like for example, people in wheelchairs, or not just like handicapped people, but also, for example, if a woman has a kid and she has a stroller, so she also needs some facility that can help her access different platforms. So it a platform should have, for example, elevators and escalators. And also it should be flexible, which means that when, for example, you have a transfer from going to one point to another, and if, for example, the transfer is like the duration to go from one platform to another to take another transport mean is not well accessed, then that make it a bit difficult for people to go from one point to another point on time. That they, especially if like they were in a hurry. So and also the timing of the different transport mean, it should match, so that like, for example, when you reach this point and you want to take the other transport mean, you should like be able to find like the good connection, that is like the optimum connection. And also it should be connected. What I mean by connected here is that like we should have real-time feeds, so that the passenger can know exactly at what time the public transport is coming, and also not just the passengers, but also for the public transport operators, they also need to know like how many people they have in each transport mean. And the last one is it should be sustainable. And that means that it should be eco-friendly. And for example, like we have now electric vehicles and also electric buses, and also like bike share apps where like you have like bikes that they were set there, and also e-scooters, that you have an app where you can check if there is one that is available and you can use it whenever you want. And also there are also cars that is like similar to that. And for cars, you can also pick up other people and go together to the same, if you're going, for example, to the same destination or like somewhere within the same destination that the other person is going. And in our group, we believe that fully digitalized traffic management of a smart city is the future. So, and for that, how we want to do, like how we want to do it like smartly is that like we want it to be in control of like knowing where each passenger is and also which transport mean that passenger take normally, and also manage it to so that we exactly be able to avoid like crowded transport means, and also make it much more comfortable for the passenger to travel within the city. And for that, we are using the mobility informations from the passenger smartphones. Normally, each passenger has a smartphone now, and that's why we choose to work only with smartphone data, because it's something that like everyone has, and it's much more convenient for the passengers. And there we are integrating digital models for passengers through to check the passenger through within the city. And yeah, and now I will be presenting some of the solutions that we did to actually help monitoring and managing the passenger flow. So our contribution, as we can see here, we have like, we're only working basically with the smartphone. We take data from all the different sensors that we have within the smartphone. I will show you later which kind of sensor I'm talking about. And then we feed this data to our algorithms. And what I mean by our algorithms, we have different algorithms. We have one for transport mean identification that is able, when you give it the data, it is able to give you that if you're in a train or a subway or a tram or a bus. And there is also passenger localization. And here we're doing it not just outdoor, but also indoor. And also this change from going from outdoor to indoor. We are here only also using only smartphone data. And the last point is the point of interest identification. I will clarify. Points of interest, it represent places that people visit frequently, like home, place of work, etc. And these algorithms, after they analyze the data and process it, they give us a digital model of passenger flow. And what we can use that with is like for some certain applications, like for example, public space design. So for example, to make a platform more accessible, you need to know, like for example, if it's really much used, so then you wouldn't need to make it much more accessible for different people. You have, like as I said earlier, people with disabilities and yeah, different like case scenarios that we can have. And also for scheduling the transport mean and making it efficient for people to use it whenever they want and at any time they want. And also studying the what if case scenarios. And what I mean by what if case scenarios is like, for example, when you're analyzing like the general mobility of a passenger, you check what he does during, like, for example, winter specifically, like if he's taking more public transportation in winter or taking his car, or for example, like walking or biking, depending, this will be depending on the weather, depending on other things. And this behavior, you can check it when you analyze this user data. And here, this was an application that we did. And here we were trying to correct, because here we have two videos I will show you. Like here we have the raw data. It was taken from the smartphone, and it is. And we can see always that we have some outliers and some jumps, especially like if you're near buildings, because of the multipath. And for that, we want to like somehow manage these outliers and have the correct trajectory. And we can see here, so here, this is the raw data. This is after we process it, only using the smartphone data, basically. And you can see the corrections. Like, for example, there we had a jump, but there it was corrected and we were on the right track. And all of this we were like using like AI basically to, not just AI, but you also have other things like Kalman filters and stuff, to use the sensors to correct the trajectory. And this is another case scenario where we're studying like the transfer from like going like outdoor to indoor. And this was measurements that we did in Munich. And this was in the station of München High Height. Here we were outside. We started outside, as you can see, but because the video is too long, I just cut it short. And we went inside, and the station is actually underground. And even though that it was underground, we were able to still detect like where the person is in the station. And here you can see that I was shopping, and then after that I will go within the station to check some information, and we still were able to identify the trajectory. And this is for the part where we try to identify the points of interest. And here we were using not only GPS trajectories from smartphone, and we also had information about the transport mean that the person was using for each trajectory. And the next step was, after detecting these points of interest, that I said that they represent like home or place of work, or like places where people, where a person go frequently. And the next step, we want to predict where this person will go next based on the history of this person, because we as humans, we have a trend. We kind of have in our usually day life, like we all the time, for example, during the week, we go from home to work. So this is a pattern, and we want to use this to be able to know exactly like where the person might go next based on his position right now. And with that, you can like do like a lot of stuff, like recommendation systems, and also like managing the transportation, because if you know where the person is now and where he wants to go next, then you can give him recommendation about the fastest way to go without him like needing to like check what is the best option. So basically you can make it much more comfortable for the passenger to move from one point to another. So for example, in this case scenario, we can see here in this short video, this was a public data set. I don't know if you know the GeoLife data set. It was in Beijing, and we took the different trajectories that we have there. Some of them, they were labeled, so we knew about which kind of transport mean the person was using. And here the person was biking, and we were able to identify here like 3 main points of interest. And we saw like when we check in the map, because here we don't, like the only problem with, and the main problem with this is that you cannot judge if this work is like you don't have a ground truth point. We don't like, because these measurements, they were taken and you don't know like exactly from where the person started or not, because the GPS, as I said, it's not accurate. There is a lot of outliers, especially if you're like near buildings and also like under trees. The accuracy is not that good. And even though with that, like we tried to do some first processing and noise removal from the data to like have like, let's say, a data that we can say that we know like not exactly, but somehow that this is like right, because sometimes you have big jumps. We try to remove that, and here let me just. I want just to go back to the video. We can see here that when we start, you see that we don't have the pointer anymore. That there was like, we didn't receive anything at that certain short time. And because that means, whether it means that the person went inside a building or something. And for that, we also try to identify whenever we have like a really long cut in our signal, maybe that means that the person is inside a building. And there we identify like different kind of places that people, depending on the passenger, goes to, and we try to predict the next location. And it's working, but we need like, if we want to like know how accurate it is, we need to have our own data that is collected, but it's not easy to get access to daily life of people because of privacy issues. And now I will start talking about the identification of transport mean. And basically now, specifically in Germany, they start this 49 euro ticket where you just like, it's like you apply to it and you only pay 49 euro for each month. And you have access to all the transport mean that you have within Germany. And the problem with this is that now with this, they don't know like how many people are actually inside each transport mean, and when are like the hours of peak and everything. So sometimes you can see that the public transportation are really full, and it's not easy to manage. So how can you manage like all these problems with like where you don't know exactly like where the passenger is and what is he using? For that, it would be nice to have like models that they can identify which transport mean that the person is using, and here using only the smartphone. So I will explain you just like what we have in the smartphone. So the smartphone has like, everyone has a smartphone. So the smartphone has like 3 different axes. So we have, as we can see in the picture, we have like 3 axes. The X, which is the movement from left to right. So when you do this, then you move it around the X, or when you tilt it like this. And when you go from top to bottom, then you're actually moving it for like, this is the y-axis, and the z is when you're moving it like this. And when you do this movement, also the signal of the sensors, it changed. And the different sensors that we have within the smartphone are as follow. Like we have the accelerometer, which measure our movement, so like, and also how fast, like we can also measure from there how fast the person is walking. And we have the gyroscope, which measure the orientation and also the rotation. So but of the smartphone. So if you rotate the phone like this, it changed the orientation of the smartphone, or this. So depending on when you're walking, because normally when you're walking, when you're holding your phone, if you're turning, your phone is also turning. So that's how you know if the person turns or not. And also there is the magnetometer, which measures the magnetic field, and it measures the strength of the magnetic field. And we will see later how the magnetic field is also important to identifying the transport mean, and we can see how it's different from each transport mean. And then we have the barometer, which measure the pressure. It's actually measuring the altitude, so the barometer is actually good for identifying if the person is going up or down using the stairs. It's really good for that, and also for detecting, like, sometimes also the number of steps that you have in the stairs. And the last sensor is GPS, and that's for like location. Sorry. And for the data collection, to do all of this, we had to collect our own data to know exactly the ground truth, because otherwise you cannot rely on. There is one public data set that you can use, but it's not that much reliable. So we worked on collecting our own data, and for that we used our, as we can see here, one of our colleagues, he was taking the different transport mean within Munich, and he was using our app that was developed in our group. And here you can see the different labels. So while you're inside a certain transport mean, you click that you're inside that. And also we have activities, like whether if you're sitting or like shopping. And here, this is how we collect our data using this app. We also need volunteers, because you need a lot of data to train a model and to do to be able to actually predict or identify whatever you want. And the smartphone, basically now we're working mainly on the smartphone held in hand, because if you also change the position of the smartphone, it changes a lot the results and the analysis. Because if you put it in your pocket, the XYZ axis, as I showed you earlier, is different now, and the orientation is also different. And the data, we only focused on Munich city. So for the data analysis, like after gathering the data, this was a walk that we did. We took here a different transport mean, and here we only calculated the norm of the magnetic field, magnetometer. And here, like, this is, I can see that you cannot know where was the S-Bahn taken, or where was the S-Bahn is the train, or where was the subway, which is the U-Bahn taken. But here it gives you that, you can see here that there is some difference. Like, for example, you have sometimes high peaks, sometimes no. And from this, you can actually use it to identify the transport mean. And what we did with this is that we tried to generate the spectrogram and the spectrogram of the magnetic field, and the lighter the spectrogram is, it means that we have a higher or a more strength magnetic field. And yeah, so here this is just a general overview of like a long walk that we did, and here we took the different transport mean within the Munich city. And now I will show you exactly like for each transport mean so that you can see the difference. So for example, here the first one we see, it's the S-Bahn, which is like for us the train, and we always have in the S-Bahn this like line in between 16 and 17 hertz in the frequency. It's always there whenever we're in the S-Bahn, which we don't have in the other transport mean. But sometimes you can have it if your tram station is next to an S-Bahn station, then you sometimes see like a slightly like a small line. Like sometimes you see it there in the U-Bahn because they were near to each other. That's why we have the line there. But with the U-Bahn, you can see here it's a bit different because you have some different signal for the magnetic field, and like here for the tram also, and that's for the bus, the last one. And this is like here we can see that every transport mean has a different signature. When it comes here only, we're talking only about the magnetometer. And here also we try to check like the peaks for like certain segments that we're using, and because this is like work that is still under we're still working on this, so I will not share with you like a lot of details because this was we still didn't like publish about it. But here you can see that, like, for example, for the S1, we can see that like we have like higher peaks from the others based also on the max values that you can see the axis is really higher than the others. So from this, you can see that this feature can help you identify whether if you're in the S1 or not. More likely than it will help you to identify if you're on the bus or tram because it looks a bit similar. It's not that much change. And yeah. So for us, we're using a CNN model to identify the different transport mean, and the input is the sensors that we have within the smartphone, and in this case, we are using the accelerometer, magnetometer, and the barometer, so the air pressure and magnetic field and accelerometer. And we have like the different, we have convolutional layers and max pooling layers to or reduce the dimensionality. And yeah, we have also some dropout layers. This one thing is that this is like not the exact same architecture. This is just an example, but it's basically similar to this. And so the first part is like feature extraction from the images that we feed to the network of like the different sensors that we have. And we have the classification layers where we have the norms that they will generate you the output. And within the output here, we were only working on basically subway, tram, train, and bus, and also walking, because it's important, because whenever you want to change from one transport mean to another, you basically need to walk. And now I will show you some results. This is what's one walk that we did also like within the city, and here we can see this was like after training the model. We use the train model. So this is like unseen data, 100%. And we can see that it was detection of the transport mean was quite okay. And yeah, we still have some problems with walking because like when you're walking, sometimes you're walking and you're just standing still, and this also have some problems because when you're standing still is a bit different. And also the movement that you do with your hand, sometimes if you're shaking a lot, that also like disrupt the process of the data. And this is here here I want to show you just like for the part of walking. So for example, for walking, for the acceleration, we can see here that like when you're inside a transport mean, like the signal is a public transport. And so we have here an identifier where you can see that The true flag is like where the person is actually walking, which is represented in red. And the blue one is the predicted one, where we predict if the person is walking or not. Here, as I told you, it's not easy to like identify 100%, but because it depends also on the user, it depends on the smartphone, because some smartphones, they process data before you get it, and this is really bad because you don't give the raw data to, in here the model is not working right, because when you don't take the raw data and you take a process data, yeah, the model is trained only on raw data. And this is also another challenge. So depending on the smartphone, it also changed the accuracy of your final results. And besides that, also where you're putting the phone, as I said, now we're only doing handheld, but if you're changing the position of the phone, that will also change the output. And this is another result that we got here. We can see that sometimes it's predicting wrong. When, like, for example, Karite predict that we are in the tram, but we were still inside the U-Bahn. And yeah, we're still working on like improving it more. And yeah, the same plot down is like for the acceleration for this walk. And you can always see that when you're walking, you have more high peaks than when you're inside transport me. And what we can conclude from this work is that we are able to identify the different transport mean using only smartphone data, and that we also, there are many problems with this, is that the fact that there are no data set that you can rely on, so you need to collect your own data and optimize it and evaluate it. And the last conclusion is that our model was able to identify the different transport mean that we have of an accuracy of 89%. Yes, there are still some problems. We're still working on solving them, and yeah, maybe integrating other sensors that you have within the smartphone, because even like I only introduced you to the magnetometer, accelerometer, gyroscope, and the GNSS. But we also have other sensors like light sensors, also audio sensors. You can also use that to improve your accuracy more, and also, yeah, so there is a lot of still work in progress to do. And yeah, I will leave you just with some final results that we had. And yeah, if you have, thank you for your attention. If you have any questions, I would be happy to answer.
So thank you very much, Aicha. If you have any questions, we'll say 2 or 3 questions for moving on for the other conference.
First, thank you for the presentation. It's a very interesting topic. My question is related to, you said that one of the limitations of your AI solution was that the solution is used only in one city, in Germany. So in order to have a solution that we can use worldwide or everywhere, how can we, because it's impossible to collect data everywhere the way you showed us. So is there another alternative for data collection in order to make the application useful everywhere?
Yeah, that's a good question, to be honest, because we also are trying to work on that. We tried taking measurement in other cities in Germany. The model was still working, But the problem is that like once you go somewhere else in the world, you have other transport means that they are public, and for there it's a challenge. And yeah, we would like to start like also working on that, because for example, I remember once I did this internship in Geneva, and there they have this new transport mean, which is the trolley bus, which is like similar to tram and also a bus. So it combines both of them. And here, like when we tried and we tested on this walks for this specific transport mean, the accuracy was not that good because it's a new transport mean, and the model was not trained on it. And I think here there is a lot of work to do for like to make this working everywhere. Yeah, it's a challenge.
Okay, thank you.
Hello, I would say congratulations for publishing your paper. And my question is, why did you use specifically CNNs and you didn't use another architecture? For example, you didn't think about graph results because for transportation problems, data in graphs really it seems more helpful to get more information about for the task of classification of the transportation. I don't know how to yes, transportation.
So yeah, we actually like we worked with CNN because we want to work with images, as I showed you, like pictures of the spectrogram of the magnetic field, and normally like CNN, they say that it's the best at detecting features from images. That's why we went for CNN. But you can always use other models to see if it actually helps you improve the accuracy or not. And that's like also you can add it as an extra, like, yeah, future work, to be honest. Like, yeah, you can always try with other models and see which one is better.
Hello. So thank you for your insightful presentation. My question is related to the shortest path problem. So I've seen that you're working on transportation and so finding the short path is very useful using the techniques and so. But my question is that, or what I want to say is that it's not always the best. The shortest path is not always the best path. So we have the peak hours, we have a lot of other constraints that we can take into consideration. So my question is, how we can use like knowing the user, the means of transportation, and also how they're interconnected by finding the best path for example, to make the mobility better.
Yeah, that's true. Like, not always the short path is the best one. That's why here, like, you need to check like other things. Like, for example, if this is a short path, but like it's also depending on like the kind of the transport means that you have, like for a transfer. For example, you have a bus and you can also take a subway. Which one will you choose? So you know normally that the bus, there is a lot of traffic. Sometimes there is a lot of traffic. So you wouldn't go for a bus. Then you would prefer to go for the subway because you have that option. Here, like studying and analyzing how people actually choose which transport mean to take, it's a bit challenging because every person has his preferences. Some people, they prefer to like stick to only one transport mean to go from point A to B, even though that is like really will take them a long time. And some people, they want something that is quick. So even if they have to change from one mean of transport to the other, they're okay with it as long as they reach there on time. So this is also like another thing that you can analyze. And also here the problem is like having access to like data, real data. It's challenging always, especially like when you're abroad because of data privacy and everything. So it's not easy to do that.
Thank you.
Thanks for the explanation of this interesting topic. Honestly, I have two questions. The first one is, did you make a comparison study with the literature? And what is the view of your proposition of the topic? The second one is, what is the view of your product data? Is there anything new if you want to compare with the open access data? Thank you.
So for the first question is that our contribution, because normally when you do the state-of-the-art study and you study what others did, because I remember my first time doing that, like, and trying to do this only using like decision trees and everything. Like, yes, it gives you like a high accuracy and everything, but once you train the model and you work with that model to like give you a result using like real data, the model is really bad. The accuracy was like not even 30%. So I'm not like, I would not say that like everyone that is like doing something is like not checking if it's actually going to work or not. But for us, we want something that is like working also in real life. Like, so when you train the model, we want it afterward, after training it, to give you results that you can rely on. And yeah, that's like most of the papers that I can say, they give you like the accuracy and everything, but they didn't try to use that model, the trained model, to actually see how it works in real life. That's what I noticed. And for your second question is that when you use like an open source data, because there is one from, I think, Huawei, they collected data and they also had information about the transport mean, and it's mainly for the transport mean identification. The only thing there is like, you're not sure about if the person who did that was labeling correctly or not. Plus, yeah, you can never know, because, and also how he was holding the phone, and many aspects here would change the results. So to make sure and to actually see if like the features are working or not, you need to collect it yourself, see like how it changed from each position to the other, and also from each user to another. Because using an open data, it's a bit challenging.
اوكي شكرا بزاف لكم كاملين شكرا بزاف عائشة غادي ناخذ بتي بوز 5 minutes 5 minutes PlayStation après غادي ندوزو للسكند كلاس. Thank you very much.
the learning rate, how we choose the learning rate, how we choose the optimizer, etc. All right. Okay. So I'm gonna adapt to the talk so that most of you get something valuable from this talk. All right. So let's start with this first observation. So the graph I'm showing you here is the Llama 2 model. This is a model from Meta, right? And what I'm showing you is basically the performance of this model as we increase both the number of training tokens. So these are the number of basically sentences we use to train the model, right? Text-to-text prediction, like the ChatGPT, right? And the color code is the size of the model. So how many parameters are in the model. So we have the 7 billion parameters, we have the 13 billion, 34, and 70, right? So 70 billion is the largest one here. So there are two observations here. By the way, the y-axis here is just the train perplexity, right? Which is a measure of how good the performance of the model is, basically, right? So the lower that perplexity or that y-axis, the better the model. Okay, so two informations or two observations we have from this graph. First one is as we increase, given a model size, so 7B, 13B, if we fix the model size, we increase the number of training tokens, we see that model performance gets better and better, right? If we fix the number of training tokens and we increase the size of the model, the performance gets better as well, okay? So two things. These models, right, get improved every few months, right? And the common characteristic is we increase both the number of parameters, which is the model capacity, right? So the number of layers, the embedding dimension, etc. But we also increase the number of training data points, okay? Right. Now, the natural question is, how do we efficiently scale up these models? How should we do that? How should we increase the size of these models and the size of the training data set, okay? To improve the model, of course, right? So the goal is really just to get a better model at the end, right? Okay, so I'm gonna start with a very general figure about how do we train a model in general, right? So you can think of a model as a deep learning system. This deep learning system has 4 components, okay? So the first component is the data, of course. So the data we're going to use to train the model. This data is generally collected from the web, right? Scrapped, or each lab has some way of collecting data. But recently, we started using synthetic data as well to train the model. And synthetic data would be data generated using GPT, using Claude, etc. So this is synthetic data. Okay. The second pillar of this system is the neural network itself. So we should specify the model, right? So now we have the data, we should specify the model that we want to train. And the state-of-the-art models are just transformers currently. Transformers architectures, which are, okay, raise your hand if you're familiar with transformers. All right, good. Yeah, so these are a specific neural network architecture, but there are other architectures like convolutional neural networks. There are also recurrent neural networks, MLPs, okay? Right. Now, once we have the data and we specify the model, the first step to take if we want to train this model is to figure out how we initialize the weights in that model. So the weights are the parameters that we will train, right? And generally, in practice, we use random initialization, right? So this is a Gaussian initialization or K-mean initialization if you use PyTorch, for example, or TensorFlow. So once we initialize the weights, now we train the model. So how do we do that? We use some variants of this algorithm called gradient descent. Raise your hand if you're familiar with gradient descent. Okay, that's good. So one variant that is very successful currently is Adam. It's basically just momentum. It's called momentum gradient descent. It has some history gradient set, and then we normalize and we get this Adam optimizer, right? It's really just a variant of gradient descent. Right. So the training algorithm, as I said, we choose some algorithm like Adam, and for that algorithm, we choose what we call the learning rate. This learning rate will define basically the size of the step we take during training. Okay. So at each step, there's a size called the learning rate. Okay. Right. So now we know how to train a model. We want to scale the model now, right? So this is the goal of every industry lab currently, from OpenAI to Anthropic to Google to Microsoft. They are all working on this actively, trying to figure out what is the best way to scale these models. How do we increase the size of these models in an efficient way to ensure that we improve performance optimally in some sense, right? So given the compute budget that we have, given the GPUs that we have, etc., how do we scale up these models to achieve the best possible performance? Okay. Right, and by model scaling here, I forgot to mention this, but model scaling, just as you might have already understood it, it's just really just how to scale the data set size, how to scale the model size, okay? So in this talk, I'm gonna focus on scaling model size. I'm gonna forget about data. It's another topic that has a lot of literature. So I'm gonna focus only on scaling and model size, and hopefully you'll get something useful from this. Okay, so what do we mean by scaling model size? So most of you are familiar with transformers from what I saw. So transformers have this embedded layers, right? It has the embedded layers, has the transformable blocks, right? Consists of attention models, MLPs, etc. So you repeat these hidden layers, and then you have this projection layer. So the number of layers is called the depth of the model, right? So number of layers. So you can scale that. You can increase the number of layers, right? By increasing the number of layers, you increase the number of parameters in the model, so you increase the capacity of the model. But you can also not increase the number of layers and just increase the embedding dimension, right? This is so in for example, if you're familiar with GPT-2, the embedding dimension is like 700 something. You can increase it to 2,000 or something like that, and then retrain from scratch. Okay, so now the question is, and this is the question I'm gonna try to address in this talk, is as we scale this model, as we increase capacity size, how do we adjust all these components that I told you about, initialization, training algorithm, architecture, such that the model I obtain after scaling that model, right, is better than the current model, right? So this is the question, because after all, what you want to do is you want to improve performance, right? So you want to figure out how should we adjust all these components here such that I achieve the goal of improving the performance, okay? So this is the question, right? So I'm gonna give you an example of just a general neural network. Don't worry about the math here, it's very, very simple. So you have the input layer, Y0. So this is usually, in transformers, you call this embedded layer, okay? And then after that, you have these hidden layers that will consist of multiple blocks. So in transformers, it's just, as I said, self-attention plus MLP. And convolutional neural network, that's a convolutional layer. And an MLP network, that's just an MLP projection, etc. Anyways. So these parameters here, W0, W1 to WL, these are the trainable parameters. These are the parameters that we will train to make the model learn the data, basically, okay? And here, model size, as I said at the beginning, is controlled by two parameters. The first parameter is the width of the model, or the embedding dimension, okay? So this is the dimension of this hidden layers YL. And the second parameter that controls the number of, or that controls the model size is the number of these hidden layers, right? Okay, so that's the depth, L. So in this talk, I'm gonna use this notation. The width is n, so the dimension of the hidden layer, and the depth is L, which is the number of those hidden layers. Okay. Right. So I'm gonna further focus on one simple way to increase model capacity, and here I'm gonna focus on depth. So what happens when we increase the number of layers in a model? Right. This might be useful for you, I think, in this hackathon if you're gonna train models and increase the number of layers. Okay. So how to do that in an efficient way? Right. So I'm going to consider this simple example of a neural network. It's called vanilla ResNet. So basically, you have the input layer, and the hidden layers are just given by this simple formula here, right? So you keep to build the next layer, you just keep the previous layer, and you add this transformation here. So WL times some activation function, right? Reload, for example, right? Applied to the previous layer. And after you do this for capital L times, which is the depth, you just compute the output layer, which is the projection. That's it. Okay. So here the depth is capital L, so this is the number of hidden layers here. The width is n, which is the size or the dimension of this YL. So YL has dimension n. Okay. And the activation function is phi here. So it could be a reload, for example, or hyperbolic tangent, or any variant. Okay. It's just more generally, this ResNet or residual neural network architecture has this general form, right? So you can, instead of just using this simple mapping here, you can think of any general mapping to put it here. And by the way, transformers are also ResNets, right? So they're part of this family of architectures, okay? Right, so let's look at this before, okay, let me explain what this is first. So here, I'm considering this simple vanilla ResNet, as I introduced before. What I'm going to show you here is the behavior of this neurons, YL, as I increase the depth of the model, so the number of hidden layers, okay? So here, n, the width, or the dimension of YL, is just 8. So that's why you see 8 dots here, okay? Now, I'm going to show you what happens to these dots, or these neurons, or basically the nodes in YL, the neurons in YL, as I increase depth with this simple architecture. Right, so let's do that. Yeah. Right. Can you tell me what you see? What's the problem here? Can I give you like 20 seconds to see? What? Random. Okay, let's say that's fine. That's not a problem here. It is true that they're random, but yeah, for the simulation, they're random. Yeah. But there is a much bigger issue. Exploding, yeah. So you see the values on the y-axis, they're growing exponentially with depth, actually. So as we increase depth, basically the values of the neurons in this hidden layer grow exponentially large with depth, right? So this is problematic because in practice, this implies that you have numerical instability. So the model does not train well, actually. So what happens if I do this simple, okay, so basically this is just what I said. So from here we see that we have this exploding features. So features are just YL. And we can show that in this case also we have exploding gradients if we compute the gradients. And that's problematic for training, okay? Now, what I'm gonna do is simple. I basically, so let me go back to the previous. So see this architecture here? I'm just gonna introduce a simple factor here in front of this block. So 1 over square root of depth. Depth here is capital L, so the number of layers, okay? So you see that the behavior completely changed. So I didn't change anything. I only introduced that, factor in front of the residual block. Okay. And now the values of these neurons are stable as we increase depth. Nothing explodes actually. Right. Okay. So what do you think we should use if we want, like which network we should use if we want to increase depth? This one or the previous one? Yeah, because the features are stable, gradients are stable. This makes more sense, right? But how do we justify this mathematically? We just introduced this scalar here, and we have a completely different behavior, completely stable gradients and features. So how do we justify that? Right, so I'm going to show you something here, but don't worry about the math. So if I consider this general resonate here that has some scaling factors lambda, some general scaling factor lambda, then we can show something, a theorem basically, that says that, so don't worry about this expectations and stuff. This just means that the average value of the neurons, and this is the average value of the gradients, okay? So don't worry about the math there. It just means that these two things are proportional or of the same size as the exponential of 1/2 sum of this scaling factors lambda, okay? So these scaling factors, we introduce them in front of the residual blocks, right? So this is the the mathematical results, but from here, the use case would be, okay, so I want to increase the number of layers so that I get a better performing model. But at the same time, I want to ensure that as I increase the depth of the number of layers, nothing explodes, nothing happens, nothing bad happens in that case. And one way to do that is by looking at the magnitude of the features and the gradients with respect to depth as we increase the number of layers, right? And this is what we do here. And basically from this, okay, I'm going to ask you this question actually. So from this results, that tells us basically that the average magnitude of the neurons and the gradients is proportional to this thing here. So what should we do if we want to increase the number of layers to make sure that the features and the gradients are stable? How should we choose the lambdas? Do you have an idea? Yeah. You can do that, but the weights will be changing as you train the model. But something that is really independent from the weight, the weights. What would it be? The depth, yeah. You can think about the depth, yeah. So basically, the general result from this is that as long as you choose the scaling factors here, such that this sum is bounded, right? It's bounded in the sense that it doesn't grow as you increase the number of layers, then you can safely increase depth. You can safely increase the number of layers, okay? So I'm going to show, and this is what we call a stable resonate. First example is the uniform scaling, and this is what I showed you in this simulation, 1 over square root of depth. So if you choose lambda to be 1 over square root of depth, capital L, so what is this sum in this case? If you compute the sum of lambda squared, what is it equal to here? L, it's lambda squared. One, yeah, exactly. So the sum here is 1. So if you do lambda squared, you have 1 over L, and you have a sum of L terms, right? So it's L times 1 over L is equal to 1. Okay. So in this case, that boundedness property is satisfied because that sum is always equal to 1. But you can also think about other choices of lambda. So don't worry about that right now. Let's just focus on this one. Now I'm going to show you the empirical results with this. So here I'm gonna train that vanilla resonate that I showed you before. I train it on Cypher 10 dataset, which is an image dataset. with Adam W, which is an optimizer. So I'm showing you two figures here. The one on the left is without any scaling, so lambda is equal to 1. This is the standard implementation in PyTorch, TensorFlow, etc. And the one on the right is what I'm suggesting here, so the 1 over square root of depth that I showed you, okay? The color code here is basically the depth. So the brighter or the darker the model, the darker the line, the deeper the model, okay? So we have models from L, so depth equals to 2 to the power 3, to L equals to 2 to the power 10. So from 8 to roughly 1,000 layers, okay? So you see here the log loss, right? The training loss as we increase the depth. And here the x-axis is just the learning rate. So for different choices of learning rates, this is what we get. Okay. So the difference is clear here. With standard ResNet or the standard implementation in PyTorch, if you keep increasing the number of layers, at some point the model doesn't train actually. And this is because of that exploding behavior that I showed you at the beginning. The gradients explode, the features explode, so the model cannot cope with that behavior, so it doesn't train at all. You're stuck at a very trivial accuracy, okay? With the stable ResNet, simple modification of the ResNet, just introduces 1 over square root of depth, you see that the model keeps improving as you increase depth. So for the largest depth here, which is roughly 1,000 layers, you know, it achieves the best performance. Okay, right. So these are two things, but I'm gonna stop here for like 1 minute and ask you if you have any questions, because the next thing will be a bit more. Do you have any questions? Yeah.
In the non-controlled case, in the bit standard case, is there like a sweet spot that we could still look for in terms of tests beyond which we have this extraordinary range, or is it like schematically if you go in more depth, it's worse, or is it the sort of sweet spot we should find and then it becomes worse?
So for smaller depth, so as you can see here, for smaller depth, you see that the model is trainable with the standard range. But there is no like hard threshold or anything. So you see that performance gets worse and worse as you increase the model. At some point, it doesn't train at all. That should be related to numerical precision of the machine, etc. I think. Okay. Any other questions? All right. So yeah, so the conclusion is clear. If you want to increase the number of layers, make sure you scale the residual blocks, right? Otherwise, your model will not be trainable if it's too deep. Okay. So this is the first conclusion. Now let's just look at this figure that I showed you in the previous slide. This is for the stable ResNet with the scaling, right? 1 over square root of depth. So something we see here that really bothers practitioners is that the optimal learning rate. So what is the optimal learning rate? Basically, it's the learning rate that gives you the best performance. Okay. So for this depth, for example, 8 here, the optimal learning rate is this one. Okay. For this depth, the optimal learning rate is this one. For this depth here, like the deepest network. Sorry. The optimal learning rate is this one. Okay. Is that clear? Oh, you cannot see the curve. Oh, okay. Yeah, that's gonna be challenging. Is there a pointer or something? Okay. Anyways, so if you look at the x-axis, so that's basically what you're gonna use to determine the optimal learning rate. Okay. So for each curve, let's say the deepest one, so the darkest one, The optimal learning rate is around, in logarithmic scale, is around minus 3.5 or something like that, right? In the x-axis, you see that? So that's like the lowest point on that curve. For depth 8, so that's the lightest or the brightest color, the optimal learning rate is around 0 in logarithmic scale. Okay, is that clear? Right. So that's what I wanted to basically to specify. So this is I said at the beginning that this is something that bothers practitioners because basically as you increase the model size, right, as you increase the depth of the model, you always have to find the optimal learning rate again, right? Because that optimal learning rate shifts, right? It's not the same as you increase the model depth, okay? So from here, first of all, we see that the optimal learning rate seems to be decreasing with depth, right? From this figure, so it's decreasing, which means that that optimal learning rate should also scale in some way with depth, right? So can we express that learning rate in terms of depth and avoid having to tune it every time we increase the number of layers? Okay, that would be great. Right, so this is what we call depth parameterization. And basically, instead of looking just at the network, at this residual block that I showed you before here. So here I chose, in the simulation, I chose alpha equals to 1/2. That's 1 over square root of depth. But we can think about a general scaling, L to the power minus alpha. But now we have also, from the previous slide, we saw that the optimal learning rate seems to be shifting with depth, which means we should also parameterize the learning rate with depth. We should also express the learning rate as a function of depth. Okay, and this is what I do here. So I express the learning rate as some constant eta times depth to the power minus gamma, right? So L to the power minus gamma. And this alpha and gamma parameters, this is just a definition, are what called depth parameterization or just network parameterization. Okay. So I'm gonna, so the math to show the next result is very technical, very involved, so I'm not gonna talk about it. But basically the conclusion is that the optimal choice of alpha and gamma is 1/2. Okay. So if you want to scale the model, increase the number of layers, make sure that as you scale that model, you introduce these scalars in front of the block with alpha equals to 1/2. But also in the learning rate, you scale the learning rate as you increase the model, meaning that you will decrease the learning rate as you scale the model. Okay. And gamma also here is 1/2. Okay. So I'm going to show you some empirical results here. So basically, this is the figure I showed you before. This is the same. So the one on the left is the figure I showed you before, where we didn't scale the learning rate. So we just increase the number of layers. We scale those blocks in the residual neural network, and we increase the size. And we saw that the optimal learning rate shifts with depth, right? It shifts towards the left, meaning it decreases. Now, if instead of doing this, I parameterize the learning rate with depth as well, so I scale the learning rate as well. Now the learning rate is something like eta times L to the power minus gamma. So if I choose gamma equals to 1/2, so the optimal parameterization that I told you about, you can see that as, so this is on the right figure, as we increase depth, it seems that the optimal eta seems to be the same at some point. It converges actually, okay, with depth, which means that, for example, if you want to train a model that has 1,000 layers or 500 layers or something like that, you can just find the optimal learning rate, the optimal eta, for a much smaller model, like 64, depth 64 or something, and use that same learning rate for the larger model. You don't need to tune the learning rate on the larger model, which is very, very convenient from a computational perspective. So we call this hyperparameter transfer, which means that optimal learning rate will transfer across depth. So the same will be the same optimal hyperparameter basically. Okay, so I can show you some results also with transformers. So this is transformers architectures. This is a Megatron architecture from NVIDIA, trained on this data set called Common Crow with the Adam optimizer, learning rate eta. So you see also here that as we increase the depth of the models and the number of hidden layers, that optimal learning rate tends to be stable. Okay. So just to okay, so before summarizing this, okay, let me just yeah, show you that. So basically, the summary, or if there is like one thing you should, remember from this talk is stable resonate ensures that features and gradients do not explode at large depth. So if you introduce that scalar in front of the blocks, 1/squares of depth, and the same thing if you parameterize the learning rates with the depth, so 1/squares of depth as well, you will see that constant in the learning rates tends to be stable as you increase depth, right? So you don't need to tune that eta for the large models. Okay. I'm gonna stop here and yeah, just see if you have any questions. Yeah.
So one question is about the optimal value of alpha. So it's 1/2 minus 1/2. So it's the same that we tried before, like 1/square root of L. And this was because we choose to bound with 1.
Yeah.
So this means that this is the optimum. We should bound the magnitude of activations or gradients with 1. This is
that's one of the reasons, yes, but there is also the learning rate. And the learning rate in that case could change a lot of things. But that's the right intuition for alpha, yeah. Basically, if you choose alpha larger than 1/2, that sum will go to 0 as depth. So you lose some expressivity in the network. Okay, right. So just to give you a general idea of how do we use mathematics in this field, so I'm going to talk about like a theory of scaling. So this is a more general problem. So think about any model in AI, or it could be any general model actually. So this model will have what we call scalable dimensions, right? These are dimensions that you can scale, you can increase to improve the model, okay? So for example, in a neural network, this would be the embedding dimension, right? So the dimension of the hidden layers could be also the number of layers, L. Could be also the number of training data points. It could be the number of training steps. So we train the model for some number of steps, right? It could be context length for large language models. It could be also the vocabulary size, etc., etc. So if you think about any model, there is what we call the scalable dimensions, and basically you can always you would always want to scale those dimensions to improve the model performance. Okay. So the theory of scaling basically consists of given some scalable dimensions S1 to Sk from this set of scalable dimensions, right? We want to study the limit of what happens to the network, the model, as these scalable dimensions go to infinity. So basically all the mathematical results I showed you are derived in the limit when the depth, the number of layers, goes to infinity, right? And by understanding that limit, you get to derive optimal choices or optimal ways of choosing your hyperparameters. So for example, with that analysis, we found that you should scale the number of, we should scale the residual block, should also scale the learning rate, etc. So all of these results are part of this theory of scaling, where you study the limit of the model of the system as the scalable dimensions go to infinity. Okay. So just to, if you are interested, These are the references if you want more details, of course. So most of these references are, contain the mathematical details, so the proofs, etc. So they would require some technical knowledge. But yeah, this is if you are interested in the details. So this is for depth. This is what I talked about in this talk. So scaling the number of layers. But there's also other references about, for example, scaling the width of the network. So the embedding dimension. How should we do that optimally? So there's this a nice paper by one of my co-authors. And some of these results are currently used by GPT models, for example. Okay. Also, for those of you who are interested in fine-tuning, not just pre-training, there's also this theory for fine-tuning with low-rank adaptation, etc. Okay. So I'm gonna stop here and ask you if you have any questions. And thanks. Sorry. This one? Sorry? Okay.
Thank you very much, Sofiane. Et j'ai une question vraiment. Hello, Mr. Sofiane, and thank you for your presentation. I just want to ask you about this fine-tuning method, since I have used this before, and I don't have lots of details about it. If you can just give us a brief summary or something.
Okay, so so you know LoRa method, okay. So yeah, for those of you who don't know LoRa, this is like probably the most successful fine-tuning method right now, where instead of doing the full fine-tuning on the model, you just add like a low-rank perturbation, train that low-rank perturbation. So to answer your question, basically the current way of using LoRa is you set some learning rate to some learning rate, and you train those A and B matrices using the learning rate. So we found that doing that is suboptimal, and what you want to do is choosing different learning rates for B and A matrices. So that's LoRa plus. So in the paper, we show that basically the learning rate for the B matrix should be much larger than the learning rate for the A matrix if you want to optimally fine-tune the model.
And what about QLoRa?
Same intuition should apply in that case. QLoRa is just quantized, right? So yeah, same intuition.
What do we actually quantize? The weights or the else?
In QLoRa?
Yes.
So in QLoRa, you quantize the weights, right? So the A and B matrices. But the issue is that you still need to compute the activations in FP16 precision. Otherwise, that's going to be hard to compute gradients and stuff. But yeah, so QLoRa, the same intuition should apply in QLoRa as well. Integrated with Llama Factory, if you know. So in that package, it's already integrated, so you can just import it there. But with PEFs, it's still in the process, yeah.
Okay, thanks. So just I would like to understand, like, does it apply two different learner rates on the A matrix and B matrix, or does it apply like two different learner rates and a customized optimizer on the B matrix as well? Because I've seen some online implementation, and they were implementing like a customized optimizer on the B matrix itself.
No, it's really the same optimizer, but different learning rates for A and B. Yeah, that's it.
Do you have already a repo on GitHub like with
Yeah.
already implementation?
Yeah. So if you look at the paper, there's the code there. You can access it. It's open source.
Thanks.
Assalamualaikum. First of all, thank you so much for this presentation. It was really insightful. I just want to ask, like, I don't know if this is out of context or whatever, but for like research papers, once they're accepted, for example, in a big conference or something, do you guys contact the technologies, for example, stable ResNet, once it's accepted? Do you contact, for example, PyTorch, so it can be included as a function or something like that, so other developers or other machine learning engineers can use it, or like, what's the process of it?
So for stable ResNet, we didn't do that, but we're trying to do that for the last iClear paper, where we parameterize both the block and the learning rate. Unfortunately, yeah, it's really hard to change, community perspective on this stuff. I think big labs right now are aware of this issue and they're using this scaling stuff. So you might not find it currently in PyTorch, but it's really easy to change. If you want to change it in PyTorch locally, you just access the ResNet or transformers implementation, you add that scalar. It's really easy.
Thank you.
You're welcome.
Thanks for the presentation. I have just one question about the use of the LoRa in the topic of, for example, image classification. If you have uses in this topic, how can we can apply it?
So I know LoRa is used in diffusion models. So when you say image classifications, you mean you have a pre-trained image classifier and you want to fine-tune it on some smaller data set? Yeah, I have never seen like such application, but I'm sure it would work, I think, in that case, yeah. So I saw applications in diffusion models, so the models that generate like images and stuff. But currently, I think the most successful application of LoRa is in text models. Yeah.
So, hello.
Hi.
So, thank you for your presentation. It was really insightful. It's very rare that people actually we see the details of how transformers work and how we can make a great use of them. So, my question is really about, so I'd say, similar architectures or the other research that also for large models. So, we saw recently architectures like Mamba, or people reintroducing RNNs or LSTMs with slightly bit differences, but they're giving good results. So you personally, what do you think of the potential of using similar architectures, and how can they, I'd say, not replace, but can be used also as the transformer architecture?
Yeah, so for recurrence models like LSTMs and XLSTMs, which is a recent paper, right? Or Mamba or Java, which is a hybrid model. So the issue is just that basically these models, especially recurrent neural networks like LSTM, were never scaled before. They were not scaled before. So people started scaling transformers and found that they work better, and they just use them for until now. Currently, there is some interest in scaling recurrent neural networks, and it seems that if you scale it enough, it matches transformers performance. The good thing with LSTMs and recurrent neural networks is that the inference cost is really much cheaper than with transformers, because you don't need to compute the attention and stuff, which is quadratic and sequence line and stuff. So yeah, they definitely have some good properties like recurrent neural networks. I'm sure that there will be tasks where transformers are better than recurrent neural networks in the opposite and vice versa. So it's not something that will completely replace transformers, I think.
So hello, thank you for your presentation. I just wanna which are the best way to functioning a lesson diffusion model like stereo diffusion or playground, which is the best way to function this model?
So currently, LoRa is definitely one of the methods. LoRa seems to give very good results. So LoRa was introduced as a fine-tuning method for text models, but recently, in the last 1 or 2 years, it seems that the diffusion models community were using this LoRa to fine-tune the model. It seems to get very good results.
Il y a l'impact, une dernière question. Thank you pour une dernière fois, Monsieur Sofiane. Dernières informations. Donc, d'abord, qui d'abord, Inch'Allah. Challenges يبداو ثلاثة دونك نتسناوكم مع جوج وربعين دقيقة في البلاصة اللي كنا البارح سميتها أغوغا. Thank you everyone.
Non, ما سمعتش. لا لا tranquille. Okay, then.
نحبس هذا ديال الدراري انا غناخذو انا سمعت
صراحة صبية تبارك الله.
البلاصة كنا البارح
كنا في الليل ذاك البلاصه خلي هذيك
لا لا ديك السنة
ديك شحال اسمها
لا والله خصني نتكلف انا زاد ديال مولاتي ديك ديك